As another example, I'll solve for you exercise 54 from the end of chapter 7. You should probably take a look at it and read it carefully. And as we've been talking, the first step, of course, is to draw a picture. So if you haven't drawn a picture of the situation, you might want to go and do that and try it yourself. Here's what I get. The problem is about a skier who's skiing along on a level surface above a hill, a little downward hill. Initially, the skier's going 6.5 meters per second, and they're also given the fact that the skier's mass is 62 kilograms. As the skier is going along, he encounters a rough patch of snow. The rough patch is 3.5 meters long, and the coefficient of kinetic friction along that rough patch is 0.3. Then the skier encounters a little downhill. The height of the downhill is 2.5 meters. And part A of the question is to figure out how fast is the skier going at the bottom of the hill. We're only going to do part A. There is a part B, but I don't think it's really very interesting. So the first step in doing part A is to ask yourself the question whether or not a conservation of energy approach would work best or a work kinetic energy theorem approach would work best. What do you say? Well, I say it's a work kinetic energy theorem approach because there's work done by friction along this rough patch, so the initial energy and the final energy are not going to be equal to one another. In fact, probably going to have a little less energy here than here because friction will sap some energy from the skier as he goes over the rough patch. So to do part A, after talking about all of those things, the starting point is to realize that the total work done on the skier's got to be equal to the skier's change in kinetic energy. And then you sort of work both sides of this equality. On the left-hand side, asking yourself the questions, which things do work, and try to calculate the amount of work. And on the right-hand side, calculate the initial kinetic energy, which you can use to find the final kinetic energy. And once you have the final kinetic energy, you're going to get the final velocity. All right, so let's work on the left-hand side of this first. Let's ask ourselves the question, which things do work on the skier from here at the top of the hill before the rough patch to here at the bottom of the hill? So I see two things do work. Friction does work and gravity does work. So we're going to be able to figure out, in this case, a number for each of those things. So for friction, since the force is constant, you're going to be able to use the Fs cosine of the angle formula to calculate the force of friction. In this particular case, we need the kinetic friction force, the distance over which that force acts, but we have that, 3.5 meters, and we need the angle between the kinetic friction force and the displacement, s. So I think you can probably see that the angle between the kinetic friction force and the displacement is 180 degrees. Think about it. The skier moves to the right, but friction along this rough patch is directed to the left. So this one here, the cosine phi, is just going to give us a -1. So that is going to be -1. Then we're left with trying to figure out what is the magnitude of the friction force. Well, on a level surface, you probably remember enough from the last chapter to realize that the kinetic friction force is equal to the coefficient of kinetic friction times the normal, but on a level surface, the normal is equal to the skier's weight, so mg. And then left with the s, and we're left with the -1. So if you take the coefficient of kinetic friction, the skier's weight, s, which is 3.5 meters, and hit it with a -1, you should be able to convince yourself that the work done by the friction force is -638 joules. I'll include this 0.0 because it's a 3 sig fig problem throughout, so for these intermediate things I'll have 4 sig figs. So you should check to see whether or not you get the same number there. Now we want to calculate the work done on the skier by the force of gravity. Well, the way to get the work done by gravity is to use potential energy because it's a conservative force. So the work done by gravity is equal to minus the change in potential energy, which is U initial minus U final. So initially, the skier is 2.5 meters above where he is finally. So if you set the zero level, the y equals 0 level, to be where the skier is at the bottom of the hill, then the initial potential energy is equal to 0. Oh no, I'm sorry. I wish I could edit these videos, but I totally just messed that up. The final potential energy is equal to 0. I'm sorry about that. So we got U initial minus U final, but when the skier is at the bottom of the hill, the final kinetic potential energy is 0. And the initial potential energy is just mgh. So the work done by gravity is equal to plus mgh, which is a number you can calculate also. And that turns out to be 1,519 joules if you plug in the numbers. I hope maybe you pause the video and calculate those yourself. So now we know what the total work is on the skier. It's the work done by friction, which turns out to be negative, plus the work done by gravity, which turns out to be positive, and it's greater. The work done by gravity is positive and a little bit greater than the work done by friction. So I think at the bottom of the hill, the skier is going to be going a little bit faster. So you can calculate the difference between those things, and you get 881 joules, and it's plus. So now how do you answer the question about how fast the skier is going at the bottom of the hill? Well, the total work has got to be equal to the change in kinetic energy, final minus initial, so 1/2 mv final squared minus 1/2 mv initial squared. And you got numbers for all of these things. The total work, 881 joules. The mass, 62 kilograms. And the initial velocity is 6.5 meters per second. Why don't you try to plug in the numbers and do the work and see if you can confirm that the final velocity after you do the arithmetic is 8.41 meters per second. There is a part B, which asks something about internal energy. And we've never talked about internal energy, and I don't really think it's important in this context. But what is important in this context is to compare the total energy here, which has both kinetic energy plus potential energy, and here, the final energy is going to be equal to just kinetic energy. Which one of these do you think is going to be greater, or do you think they're going to be equal? Well, we'll treat that as a rhetorical question because you can't really answer me, obviously, but the thinking is like this. If it weren't for this rough patch, then gravity would be the only thing doing work and energy would be conserved, so the initial would equal the final. But this rough patch causes the skier to lose mechanical energy due to the friction force. So I think if you actually calculate a number for this and calculate a number for this, you're going to find that they're not equal. In fact, you're going to find that the final mechanical energy is less than the initial mechanical energy, and the difference between the two is the amount of non-conservative work that's done. That's what the problem refers to as internal energy. But if you want, you can calculate the amount of non-conservative work done on the skier. It'll be the difference between the initial energy and the final energy calculated in the usual way.